Okay, let's begin. So we're pretty much in 5.3 now, as you were mentioning. That's where we're going to be dealing with the graphs. And this stuff, let's see. The calc sequence is being rearranged as we speak, so sometimes I mislocate things. But I'm pretty sure this is still true. What we're going to do today is going to be important, of course, for your final. And then you're going to go into Calc 1, and you're kind of going to forget about it. But any of you who are going to Calc 2, it's going to come back up, and you're actually going to want to remember it. So you can just make a note of that. You're going to cover a topic called polar coordinates. And this kind of thing is going to come back. We want to know how to graph trig functions very well. So this is 5.3. And so we're talking about the graphs of trig functions. We actually already started this. Recall, last time we looked at the function y equals sine of x. Now x here, of course, represents an angle, but because I'm putting it on the xy plane, I might call it x instead of theta. And we saw the main, what we call the principal period of this graph. It starts at 0, goes up, goes down, comes back, hits 0. And this pattern pretty much repeats forever, but this is called the principal period between 0 and 2 pi. That's us revolving around a full circle. It hits the peak, which is at 1. That happens at pi over 2. This hits 0 at pi, that hits -1 at 3 pi over 2, and then it hits 0 again at 2 pi. And we also saw y equals cosine of x. And again, these are graphs that you should have memorized. It starts at 1 when x is 0, and it pretty much behaves like the sine, is just slightly shifted. And so this here is 3 pi over 2. In fact, this is the cosine graph. It's 0 at all odd multiples of pi over 2. Here's where it's at pi. And it also hits -1. So this would be the y-axis, that would be the x-axis. But again, you tend to think of the inputs into a trig function as angles, right? We also saw y equals 10x. Its main period happens between pi over 2 and minus pi over 2 because it involves a division by cosine. So when cosine is at pi over 2 and minus pi over 2, you hit 0. So your function does not exist on that line. And you kind of have this pattern repeating also forever. This shoots up to infinity, down to -infinity. That's your y, that's your x. Now, we want to sketch transformations of these graphs. Right? And by transformations, it means we're making algebraic manipulations to this function, and we want to see how the picture behaves, right? So if you were to take all the x values and subtract a number, what would happen? Or if you multiply this by a number in front, what would happen? Or if you add a number to this, what would happen? Well, again, this is just like any other function, so pretty much everything that we kind of already know how things are going to be affected here. If you multiply by a number that's larger than 1, you will stretch it vertically. If you multiply by a number smaller than 1, you will shrink it vertically. If you add a positive number to all x coordinates, this will shift it to the left. If you subtract the number from all the x coordinates, this shifts to the right. All those things are still true. One thing though It's very nice to apply these to these trig functions in general. I can give you like a general formula that can describe all these movements for you in one shot. Because trig functions are very regular, right? You have this pattern that's repeating, nothing crazy happens, they're continuous for all functions, there are no breaks, no gaps, no holes. They're very nice functions, and as we call it, they were periodic. So this pattern repeats, it's very predictable, and so I can tell you about all the transformations pretty much in a single formula, which is what I will do now. So, I don't know what to call this topic, but suppose y equals a sine k x minus b plus c. Exactly the same things will happen for the cosine version of this function. A cosine k x minus b plus c. Where a, b, c, k are constants. And a and k are not zero, otherwise we won't really have a trig function. So, as we mentioned, this guy controls vertical stretching. This guy will actually control horizontal stretching or shrinking, right? We know that if that guy is larger than 1, if it's smaller than 1, it will stretch. Subtracting from an x value will actually shift it to the right or left, depending on what the value of b is, and adding a constant can shift it up or down. So knowing all that, we can start to say the following. So this is what you need to know for these graphs. Once you know this, and sketching any graph of that type is not going to be that bad. So here are, now we're going to introduce those terminologies that we were talking about before the camera came on. Then, the following rule. If I look at the absolute value of A, this is called the amplitude. This pretty much tells you how far you stretch up and down from the rest position. I'm going to describe this in a picture to you pretty soon. But it's called the amplitude, that's the name for it. B, it's called the phase shift. But of course, by what we know for transformations, that's a fancy word, but it really just means a horizontal shift, right? That B, that number shifts us left and right. The C is going to be the vertical shift. It's going to tell us how we shift up and down, right? This is the guy we're going to think of our baseline. I'm going to talk about that pretty soon. Now, remember the whole period of a sine function and a cosine function was 2 pi? Here we're scaling it by k. And so the period is going to be 2 pi, but it's going to be stretched or shrinked by a factor of k. Put k in the absolute values here because the negative sign will cause something else to happen. Right now we're just going to worry about the period. This is called the period. That's the length of the interval it takes for the function to repeat what it's doing. So for the original sine and cosine function, this is 2 pi, but if we multiply by a k here, that's the new period. And so, what is the next thing I wanted to talk about? I'm going to call something subinterval. I'll explain what this means. I don't even know if that's the actual name for it. It's the period over 4. Because as you'll see, sines and cosines, you can think of these graphs as coming into 4 distinct parts. And what we call the appropriate graphing window is going to be, you're going to start the graph from where the B starts, and then you will continue for 1 period. Right? So if we say sketch this graph, remember the graph will extend forever in both directions. Unless otherwise stated, you will sketch it on this interval. So let me show you exactly what that kind of means. I'm going to kind of sketch it for you in a kind of generic way, and then we'll do some specific examples. So here, let's say we are on the x, y axis. You want to think of your C as the kind of baseline, right? That's kind of the rest position, right? So knowing the C, let's say it's positive in this case, so it's shifted up here. Normally the C is where the x-axis is, but you can add or subtract to shift it up or down. So that's going to be the kind of the new x-axis. This is the new baseline, right? Now, the B, like remember that we start graphing our function from 0, but I can shift it by B, right or left. So let's say, pretend it shifts to the right, so that's going to be my B. The amplitude is how far you go above and below the baseline, right? So from this, you're going to go down by a distance A. And you can go up by that distance A. This distance A is called the amplitude, right? So that's the maximum height your graph will hit, and this is the minimum height your graph will hit, right? So you can imagine a sine function being stuck in this orbit right here, where this is the new center. Now, from this point, we will measure one full period. When does it start to repeat? It will start to repeat once you hit 2 pi over k. Okay? And that's called a period. So, now you have a window. Here's where you're going to want to draw your trig function. Now, as mentioned, there's this thing called a subinterval, which is just a period over 4. It says, basically, you're going to take this length, you're going to divide it into 4 equal pieces. And the length of each of these pieces is the period over 4. Right? So that's going to be the length of all these lines here. So this line, these are all the same lengths. Why is the period over 4 necessary? Because the sine and cosine into 4 distinct pieces. These pieces are literally defined by every time the unit circle hits one of the axes, right? So there's a point where it intersects the positive x-axis, where it intersects the positive y, where it intersects the negative x-axis, and the negative y. So there are 4 distinct parts to that graph. Last time I actually color-coded each of these parts, and I show you which part of the circle corresponded to which part of the function. It turns out that you can do this kind of in general. So whenever you're thinking of, say, y equals sine x, for example, what you can imagine is that you know the maximum it goes is 1, so you can imagine that there's some line here preventing you from going further. The minimum it is -1, so there's some line here that prevents you from going smaller. Of course, there's going to be a cutoff here, 0 to 2 pi, and what actually happens is you can cut it into 4 distinct pieces. Now, how a sine behaves is going to be determined by how you treat these 4 distinct pieces. What does the sine actually do? You have to follow the pattern for the sine. The sine function will start on the baseline, right? It will then go to the top part. It'll then come back to the baseline. It'll then go to the bottom part. It'll then come back to the baseline. This is how sine behaves. In the first section, it moves up to the maximum point. In the second section, it is going to move back down to the middle line. In the third section, it will move from the middle line to the bottom, and in the fourth section, move from the bottom back to the middle line. That's how a sine behaves in these 4 sections. Now, of course, if you were to put a negative sign, this behavior inverts, right? The sine function also has these 4 distinct sections. Did you guys get this? The cosine function also has these 4 distinct sections. It behaves kind of like a sine, just shifted. So that means if you're looking at y equals cosine, again, those are the maximum and minimums. 0 to 2 pi is the obvious choice here. And you just dissect this into 4 equal pieces. And now how would the cosine behave? Well, it starts at the top as opposed to the middle. Then it hits the middle, then it hits the bottom, then it hits the middle, then it hits the top, right? So in the first section, your cosine goes from the top to the middle portion. In the second section, goes from the middle to the bottom. The third section goes from the bottom to the middle. And the fourth section goes from the middle to the top, right? And that's how it behaves in each section. And of course, if I were to take a negative, this relationship inverts. So when you're given numbers A, B, C, and K, basically what that's doing is it's taking this, you can think of it as taking this grid and stretching or shrinking it and moving it around. Now the picture inside that grid isn't changing. It's just stuck to these 4 points, right? So pretty much no matter where this shifts, the graph is going to kind of be the same. It'll hit these 4 very important distinct points, right? So once you kind of have that idea, so you can give me some positive C, it shifts up here. A positive B shifts it over here. You can tell me the amplitude, that tells me how high and low it goes. Tell me the K, that will allow me to figure out this period. That allows me to figure out this grid right here. Now once I have that grid, if you now tell me, oh, we're graphing a sine function, and you tell me, for example, that the A is positive, then I know exactly how to draw that graph. I will start in the middle. I'll go to the top, I'll go to the middle, I'll go to the bottom, then I'll go to the middle. And I will sketch it like that. Now, if someone told me it was a cosine function, if you were to tell me that it's a cosine, do I want to sketch it right over? No. Let's do a separate one altogether. Now, if on the other hand you told me that you're graphing a cosine function, right? So you tell me what the C is, that's the new baseline. Tell me where the B shifts it, left or right. The amplitude tells you how far up and down you go. Right, and this grid here, it's not really a part of the graph, it's just a skeleton that helps us sketch it properly. You'll immediately split that skeleton into 4 parts. Here, this would be B plus 2 pi over K. And each section here will be the period over 4. And now if you told me, oh, the sketch is the sketch of a cosine, then I know exactly how to draw that graph. Especially if you tell me the A is positive, I know it's going to start at the top, hit the middle, the bottom, the middle, the top. And that's going to be the picture. Now for us, we only need to know how to graph 1 period. For a class like Cal 2, when you need it in 2 semesters, you might have to go beyond this depending on the problem that you're trying to solve. But for us, we're only going to be graphing 1 principal period. Let's actually do some examples so you can actually see with some actual numbers, see things in action here. So the graph of sine x and cosine x, you should know how to graph those by heart. But let's say I kind of mess with them a little bit. We're going to sketch the following. Y equals 2 sine of x minus pi over 3. We're also going to sketch y equals minus 3 cosine x plus pi over 4. We're going to sketch y equals 1 plus cosine 3x plus pi over 2. And we're also going to sketch y equals 1 plus 2 sine pi over 2 minus 2x. So there will be a problem on your final and on your second test that does, this is pretty much all you would have to do for that question. It's going to give you this graph and say, sketch the graph of this function. Okay? And I've seen problem types like all of these on various finals that I've been looking at. Now, basically that first set of formulas I gave you is me pretty much telling you everything. There's nothing really else to talk about. Let's just see how it's applied. So the first thing you kind of want to do is to, write it in the general form, right? You want to expose who's the A, who's the B, who's the C, who's the K, right? So, given this guy, I'm going to make sure I write it out laboriously to expose all these numbers. Clearly here is the A, that's the 2, sine. Now, remember in parentheses there was x minus b, so that's definitely the b. Who's the k? Well, the k would be 1 times x minus pi over 3. Of course, this is plus 0. So immediately now you can see for this particular problem, our a is 2, our b is pi over 3, our c is 0, our k is 1, right? Now that immediately gives us all the information that we need, right? That's going to be the amplitude. This is going to be how we shift. This is where the center line is going to be. And this is going to tell us how the period is going to change. In fact, this means the period doesn't change. It's going to be 2 pi divided by 1. So this graph will still have a period of 2 pi. Right? I will actually also compute those. Those are important numbers to check. So immediately I would see that here the period would be 2 pi over absolute value of k, so that's just 2 pi. This means that the period over 4 is going to be 2 pi divided by 4, which is pi over 2. I'm going to show you how to use that number. It should be clear after we go through one example. Okay? So I write it in a specific form, get the values to find the values. Three, you're going to sketch the grid. That's going to be your next step. I'm going to do it in a special order here. Okay, so let's actually just sketch this guy. So the first thing you want to put in is the C value. So your C is actually 0. That's the guy running along the x-axis here. That's the first thing I would say. 1, put in the C value. This is the baseline. Let's call it middle line. The next thing you can do is you can kind of swap the order of these. Put in the A value and B value. So the next thing I'm going to do is I'm going to say, okay, that's the middle. How high am I going up and how low am I going down? Well, I'm going up by 2 and down by 2. So from the baseline of 0, it goes up to 2, goes down to negative 2. So this is going to be the highest this graph will go. This will be the lowest this graph will go. Next I will put in the B value. The B is pi over 3. So I'm going to pick a random point here. I'm going to mark off not just the pi over 3. You can't really do that. I'm going to call some point here pi over 3. That is going to be the start. That's going to be where I'm beginning my graph. Now at this point, I can immediately just put in the grid, because I know it's going to cut into 4 equal sections. And I'm not a computer, so I'm not going to be able to sketch to scale anyway, so put in the grid. However, you will need to know what these numbers are, right? So this is where the period over 4 comes in. The length of each of these is the period over 4. So pretty much, if I take pi over 3, what I'm going to do is I'm going to add pi over 2 to that. It's going to give me the next number. Right? Now, of course, if I take pi over 3 and add pi over 2, what do I get? So this is 2 pi over 6. That is, of course, 3 pi over 6. So the next number would be 5 pi over 6. You'll be expected to find these numbers. It's going to be important. Then, to get to the next one, I would again add pi over 2. Now, clearly, I created a common denominator of 6. So from now on, I probably think of the pi over 2 as 3 pi over 6 for the rest of the way. Right? It'll be easier to add them. So 5 pi over 6 plus 3 pi over 6 gives me 8 pi over 6. Of course, you can simplify that. 8 pi over 6 plus 3 pi over 6, I get 11 pi over 6. 11 pi over 6 plus 3 pi over 6, 14 pi over 6. That will be the last point. Right? You'll notice that the length from here to here is 2 pi. You can double check that if I take this, subtract that, you'll get 2 pi. Right? But the period over 4 is very convenient for finding all these numbers. Once you find the b, that's the starting point. Keep adding the period over 4 times. That's what your grid is, how your grid is going to line up. Start with b. Add period over 4 times to get other numbers. And at this point, here is the 6th thing that you're going to do. Now you're going to sketch the pattern. Sketch the pattern of the trig function. Now here, my function is a sine function that has a very specific pattern. As long as it's multiplied by a positive coefficient, it will start at the middle, then go to the top, then go back to the middle, then go to the bottom, then go back to the middle. So, I know this guy is going to start here, then he's going to go up here, down here, here, and back here, and that is my graph. So that is the graph of this function, at least one period.
Why is it that you added it by pi over 2 for the subdivision?
Pi over 2 is the period over 4.
All right.
The period is 2 pi. The period over 4 is pi over 2. Which means if I divide this into 4 equal sections, the length of each section is pi over 2. So if I want to find out, if I know one number, to get to the next one, add pi over 2. Keep doing it. Other questions? Now the goal is, of course, to do so many of these, and your textbook has a lot of examples, that it becomes very natural. Of course, I don't expect you to write this out. I'm just explaining what I'm doing in what order. I think this is the best order to do it in. You can kind of switch these two, but just pick an order you like and always do it that way. I think starting off with the C value and then figuring out everything from there is a good way to go. So to sketch this graph, that's what it would look like. Let's actually do another one. So, b, y is equal to minus 3 cosine of x plus pi over 4. Again, I'm going to write it in the general form. Minus 3 cosine of 1 x minus a minus pi over 4, because there's a minus in the general formula, plus 0. Here, my a is minus 3, my b is minus pi over 4, my c is 0, my k is 1. This means that my period is 2 pi over 1 equals 2 pi. This means that my period over 4 is, again, pi over 2. So now I'm gonna start sketching this. So I'm gonna draw this guy in here. X, Y. 0 is my baseline. I know I go up and down by the absolute value of 3, which is just 3. So I'm gonna go up 3, go down, minus 3. That's the top, that's the bottom. My B is actually negative pi over 4. So I'm going to pick a number over here. Call that minus pi over 4. That's where I start. Now, we'll put in the 4 sections. Now notice, this is kind of, pi over 4 is half of pi over 2. So this is actually going to go to the other side of the x-axis. Right? So pi over 2 is going to bring this over here. So my 4 sections are going to look like that. 1, 2, 3, 1 more, 4. So what I'm going to do is I'm going to take pi over 4 and I'm going to add to that 2 pi over 4, which is the pi over 2, right? I just changed it to a common denominator. So minus pi over 4 plus 2 pi over 4 gives me pi over 4. Add 2 pi over 4, 3 pi over 4. Add 2 pi over 4, 5 pi over 4. Add 2 pi over 4, 7 pi over 4 is where this guy will end. Now that I know that, I am simply going to sketch the pattern of the cosine graph. However, notice that there's a negative sign. Negative means it will flip everything upside down. So instead of starting from the top, it will start from the bottom. Then it'll go to the middle, then it'll go to the top, then it'll go to the middle, then it'll go to the bottom. So that's that graph. Now, these points are going to be important for us to be able to find. It's pretty obvious what the x-intercepts are, but there are cases where it's not obvious, but we have to talk about solving trig equations before we can find them. But we're coming back for solving that pattern. Right now, I just want you to see the pattern. Yeah.
Isn't it like that because it's negative? Because the first one you showed us. Isn't it like that because it's negative?
Yes. So a regular cosine is like this, right?
Yeah.
That's your cosine. So if you have a negative cosine, it must flip upside down. Right? Because multiplying a function by a negative number reflects over the x-axis. Other questions? Let's do it again. C. First step is to write it like the general form has it. So this is y equals, this is 1 cosine. Now notice here, I have a 3x. In the general formula, I don't have 3x, right? It should just be x minus b inside the parentheses. What can I do here? Just factor out the 3. Factoring out the 3 gives me this. This will be left over with x plus, what would this be here? If I factor out 3. Pi over 6. Right? Remember, when you factor something out, you just divide everyone by that thing inside. Now, of course, positive pi over 6 is kind of weird. We think of this as negative minus negative pi over 6. And here our c is plus 1. Here I get my a is 1, my b is minus pi over 6, my c is 1, my k is 3. This, of course, means that the period is going to be 2 pi over 3. And this, of course, means that the period over 4 is going going to be pi over 6. So my C is 1 in this case. So the first thing I'm going to put in is that 1. That's my center line. From that point, my amplitude is 1, which means from that point I'm going to move up 1, brings me to 2. I'm also going to move down 1, which brings me to 0. My B is minus pi over 6. Pick a random point over here, call it minus pi over 6. Period over 4 is also pi over 6, so the first dissection will happen right on the y-axis. 2, 3, 4. Each time I'm going to add pi over 6, that gives me 0. Add pi over 6, this is pi over 6. Add pi over 6, this is 2 pi over 6. Add pi over 6, this is 3 pi over 6. And now, that's the entire grid. I just want to draw the cosine graph. I'm going to start at the top, then it's going to hit the middle, it's going to hit the bottom, then it's going to hit the middle, and it's going to hit the top. That's how cosine behaves. It's the graph. Questions? Now, of course, on average for any particular problem, and like I said, this will be one problem on an exam. Any particular problem, you should be able to do it in less than 6 minutes, and hopefully with something like this, you can do it a lot quicker. Actually, they're not going to give you very ugly numbers. You know?
Why did we go up by 2? Like, why was that the max?
Amplitude is 1. The amplitude is how much would go up and down from the baseline. The amplitude defines the height from the baseline, which is the center. Right? So my C was 1. That tells me I start here. That's the C. The A is how I move up and down from the C. So I start at the level of 1. I go up by 1 and down by 1. That gives me the entire vertical line. Do it again. Again, first step, write it in the general form so that you can start to pick out the numbers. So I would start by writing this as, this is 2 sine pi over 2 minus 2x plus 1. This isn't quite in the right form. No, remember, we want the x in front and we don't want a coefficient. So what I would do is I would factor out minus 2x. Factor out a minus 2. This will leave me with x minus pi over 4. Now, remembering sine is an odd function, we spoke about that yesterday. Any negative sign, we can bring it out to the front. If this were a cosine, it could literally just ignore that negative sign. So that's the general form. My A is going to be minus 2, my B is going to be pi over 4, my C is going to be 1, my K is going to be 2. And what do I have here? My period is going to be 2 pi over 2, so that's pi. This means my period over 4 is going to be pi over 4. So let's sketch it over here. So C is my center line, that's 1. The amplitude means we're going up by 2 and down by 2. So I would move up by 2. This will bring me to 3. If I move down by 2, maybe I should draw this a little bit more to scale. So let's put the 1 here. Going up by 2 puts me at 3. Going down by 2 will put me at -1. My b is pi over 4. Pick up a spot, call it pi over 4. That's where I'll start the graph. I am going to draw 4 sections from that point. Where do these sections appear? Well, I keep adding the period over 4, which in this case is pi over 4. Pi over 4 plus pi over 4, 2 pi over 4, plus pi over 4, 3 pi over 4, plus pi over 4, 4 pi over 4, which is pi, plus pi over 4, 5 pi over 4 is where the ending is. And that's the grid. So now I want to graph a negative sine function. So that means it will start at the middle. Instead of going up, it's going to go down. It's going to go back to the middle. Then it's going to go to the top. Then it's going to go to the bottom. That's the graph. Questions? Yeah.
You factored out the -2. Why,
Yes.
Why does the negative go to the front of the entire equation?
Because last time we mentioned, sine of negative something is negative of this sign.
Okay.
And the cosine of the negative makes no difference. This was an odd function and even function. So conceptually, what does it mean to have like a negative period, right? It's conceptually it's difficult to think of, so just simplify it using a rule you know. So a negative k kind of looks weird, so just move the negative out. If it were a cosine, I could literally just ignore the negative. And that's it. Yeah.
Would we be doing tangents on the final exam?
No, unfortunately. Tangents have slightly different rules though. I can quickly tell you about a tangent. Let's start. So if you have y equals a tangent kx minus b plus c, technically the a is the amplitude. It's kind of like a vice president, it's mostly symbolic, right? Because tangent stretches from positive infinity to negative infinity. What does it mean to stretch it further? You're not going to notice it, right? But the b is also, again, a phase shift. It's a horizontal shift. The c is, again, the vertical shift. The difference here is the period. Now, for the original tangent graph, you'll notice that the period goes from the minus pi over 2 to pi over 2. That length is actually just pi, it's not 2 pi. So the period here is actually pi over k, not 2 pi. And here, you don't do period over 4, you do period over 2, is that interval you want. And that's because of how the tangent behaves. Well, the period is pi, but it really only comes in 2 halves, right? There's no real 4 sections. There are 2 sections. It hits the middle, right? And so you can do that. So if someone were to ask you to sketch y equals 3 tangent 2x minus pi over 6 plus 1. Then here, yes, your a is 3. Doesn't really matter actually. The only thing that where this will matter for the tangent is if it's negative, right? So you'll have to know to flip this picture upside down. But the vertical stretch, you're not going to notice it. Here, the b is pi over 6. the c is 1. You look for the period. This is going to be pi over the k, which is 2. And of course, then the period over 2 is going to be pi over 4. So if you start to sketch this one, the c is going to be 1. You won't really have a top and a bottom. What you would have is a left and a right, right? And how much is the left and the right? Well, it's by pi over 4. Right? So the b starts at pi over 6. And then you're going to move left and right from that. So if I take pi over 6 and add and subtract pi over 4, pi over 4 is actually larger than pi over 6, so it's going to come somewhere over here and somewhere over there, and you have that. So the length here, you'll just add pi over 4, and then for the length here, you'll subtract pi over 4. And here is where the middle of the tangent graph will sit, and then you'll just... Slightly different rules. You don't really need to know about tangents or any of the other ones. You're going to be asked about sines and cosines. Let's move on. That's pretty much all you need to know about graphing now. So you need to know the general graphs, just y equals sine of x and y equals cosine of x, what those guys look like. You also need to know how to sketch transformations. And that's definitely a problem like with sines and cosines, it's definitely showing up. You don't need to worry about tangents really. What we want to talk about now are the inverse trig functions. I'm not going to remind you about all the stuff we looked at for inverse functions. Recall the important items about inverse functions. They still apply pretty much exactly the way they apply in general here. This is how our transformations apply exactly the same way, right? Subtracting from an x is a shift to the right, adding to the x is a shift to the left. All that stuff that we know about transformation of functions is applied like conceptually in exactly the same way. The important points, items about inverse functions. Right, so this is a function that undoes a function, right? So your function does one thing, the inverse takes it back, right? And we also had these equations where f of the inverse is equal to x, and the inverse of f of x is equal to x. That's going to be important. Here, your x lives in the range, and here your x lives in the domain. So we have all that stuff. I'm not going to go back over it. Another important thing, which I'm going to use here, which is the only reason why I'm reminding you about it, f must be 1-to-1 and onto to have an inverse. Onto is not going to be, well, if we consider just the height as the interval, we can get the onto, but 1-to-1 is a problem, right? Problem. Sine and cosine are not 1-to-1. In fact, no trig function is. Right? Graphically, you can tell something is 1-to-1 if it passes the horizontal line test. We looked at that last time. Of course, obviously, sine does not pass the horizontal line test. You can have a horizontal line which will literally cut it in an infinite number of places. Similar thing will happen for the cosine, the tangent, everyone. All our trig functions, they repeat periodically, so there will be a y value that repeats itself forever. You will be able to hit it with a horizontal line in more than one point. So the 1-to-1 is a problem. And our solution to this problem is to restrict the domain. So you don't look at the entire sine function. We're going to look at a piece of it, just a piece that's very convenient to consider. So, for example, let's look at the inverse sine function. We're going to talk about the inverse sine function, the inverse cosine, and the inverse tangent. I'm not going to go too much into calculations here because at this point we don't need to know about that stuff. So we're going to keep it very light, very fun, just kind of talk about the pictures. So here, start with sine. Of course, this function looks like that, and it goes on forever. Not one-to-one. What we do then is we restrict the domain. So we're going to pick a nice part of this function that is one-to-one, that will pass the horizontal line test. We like to pick parts that includes the origin, so it turns out that they slice off of this part of the sine function. So you take that middle part, ignore everyone else. This part here is going to pass the horizontal line test. So it starts out looking like this guy. But now, you want to find the inverse function. How do you find the inverse graph? So, start with a sine. It's not one-to-one. Ignore parts of it. Take a part that you really care about. Restrict the domain is the second thing. The third thing is, of course, to reflect in the line y equals x. That's how you get the graph of an inverse function. We spoke about that a long time ago. Okay, so basically, we're going to look at this graph here. We're going to sketch the line y equals x. And we're going to mirror this around at that line. That's going to look like this. And that, ladies and gentlemen, is going to be your inverse sine graph. Now remember about another property of inverse functions. The inputs becomes the outputs becomes the inputs. Here you hit, this happens at pi over 2, and this happens at minus pi over 2. So what was on the x is now on the y's. So the peak of this is going to be pi over 2, and the depth is minus pi over 2. X and y are going to switch places. Similarly, the height of the y's, this was positive 1, that was negative 1. So now the x's are going to behave like that. The maximum this will go is negative 1. The maximum this will go is positive 1. This is the graph for y equals sine inverse x, or y equals arc sine x. This is notation. So the notation has a negative 1 power. You should not consider this to be 1 over. It doesn't apply the laws of exponents. It does not mean 1 over. It literally just means the inverse. Because we had that notation where f inverse is sometimes considered. We call it that, right? So it does not mean 1 over. Okay? We already know what 1 over sine is. That's cosecant, right? This is not the cosecant function. This is something else entirely. However, traditionally, students often mess that up, so they came up with an alternative notation of arc sine, so that students don't confuse it with 1 over. So, but, I don't know, for some reason it just never really caught on. There's some people who just like using this one versus that one. And so you might see both of these at any given time in different textbooks, in different sources. Maybe you might see both notations used in the same textbook. Do not get them confused though, these are both notations for the inverse sine function. And this is very similar notation that's used for everyone else. So you can have cosine to the minus 1 of x. That means cosine inverse whenever you see it. It does not mean 1 over cosine. And you can see arc cosine of x. And you can have tan inverse of x or arc tangent of x, etc. Okay? But this is what that graph would look like. Key facts that you need to know about this function. Its domain, as you can see from the picture, is from -1 to 1. And its range is, of course, from -π/2 to π/2. So if I ask you, what is the inverse sine of this number, and you tell me a number that is not in this window, I know you have no idea what you're talking about. Okay, what's the inverse sine of 17? Is it 15? No, it will never be outside this window. This is the highest it will go. Right? So π/2 is what, 1.5 something like that, right? So it's never going to be bigger than 2. Right? So that's important that you know the domain and range. It's an important thing to know. Another thing you should also know is, of course, if I take the sine of sine inverse, you just get x. And if I take the sine inverse of sine x, then you just get x. However, here, this must work for the domain of the sine inverse. So this is for x between -1 and 1. And this guy works for x between -π/2 to π/2. Your sine inverse function can only output values in this window. It'll never output values outside of that. Now let's do the cosine and the tangent, but I had another remark here. This will come up later. Just keep in mind everything I spoke about last time, super important. That table that tells you about what's the sine of π/6, what's the sine of π/4, all that stuff. The fact that all students take calculus where things will be negative and positive, as well as reference angles, it's going to be very important for anything mixing inverse trig functions with trig functions. You have to pay, well, you should kind of always have these things in mind when you're looking at trig functions, but especially be careful to have them in mind here. Now we can do the same sort of trick for the inverse cosine. So we'll look at computing values soon, but right now I just want you to have an idea of how it looks like, what is the domain and range, and some calculation that will be useful. So again, here's the notation. We'll get like y equals cosine tangent 1 of x, or y equals arc cosine. As always, we're going to start with cosine. Of course, we all know what this looks like by heart. That goes on forever. The piece that we like to choose here, again, we want to include 0, but we continue over here. So we would go from the 0 to the pi. This part here. That's what we do. So that causes us to restrict the domain. So function looks like this. Now this will be at 1, this will be at -1, this will hit pi, this will hit pi, This is, of course, its pi over 2. And now what you, of course, do is you reflect in the line y equals x. So we're going to have this line y equals x. And so 3, sketch it a little bigger over here. Now how this guy is going to look is, of course, all your y values will now be your x values. And all your x values will now become your y values. So 0 up to pi. And of course, notice here, the pi corresponded to the -1, so this point here is going to flip up to be at that point here. And the 1 corresponding to being on the axis, so this guy's going to go here. So it's going to look like this. And that graph is called y equals cosine inverse, or inverse cosine. I'll tell you about the facts before we move on to the tangent. So, key facts for this guy. Domain and range. The domain, again, as you can see, is -1 to 1. Range here. This guy will always output non-negative values. It will output anything from 0 to pi. Another thing, we know that cosine of cosine inverse of x equals x. Cosine inverse of cosine of x equals x. These are very specific x values though. Only if x stretches between -1 and 1, and here your x stretches between 0 and pi. Now you might ask the question, what if our x is not in that window? That's where the reference angles and all that other stuff comes in, right? So if you're outside that window, you have to figure out something equivalent to that that's inside the window. And that's how the other stuff I was talking about last time comes into play. Okay, but the basic quintessential function is this. It only works in this little box right here. Inverse tangent. This one is very important for the future. Sine inverse and tan inverse are very often used for like math problems later on, because all the trig functions, the way they behave, usually the things your professor wants to test you on, either the sine inverse or the tangent inverse is going to encapsulate those things. So if your professor wants to test you on something with a restricted domain, you use the sine inverse. If he wants an unrestricted domain, you can use the tangent inverse. If he wants to test you with the inverse trig functions, they're very two important things. So you should actually know the inverse tangent graph specifically is something that you should have memorized. That being said, you won't be tested on it in this class, but I'm warning you for the future. There's going to be, if you're sticking around with calculus, this is a function that your professor's going to expect you to know by heart. Again, start with tangent. This one's kind of easy because all you have to do is just pick the middle window, right? So ignore every other part and just take this part here. You'll notice that it will pass the horizontal line test. So you start with tangent. Restricting the domain is pretty easy. And again, you reflect in the line y equals x. here's what this graph will look like. Very important graph for you to remember for the future. Don't say Jhevon never told me. So I think now you'll do calculus with inverse functions in Calc 2. So there's going to come a point a year from now, for those of you in Calc 2, where your Calc 2 professor is going to be like, so what does the inverse tangent graph look like? There'll be silence across the room because no one's going to remember from pre-calc. You probably never see it again until a year from now. You're going to remember. You're going to say, oh, it's like this, professor, this, and these are the points in it. Like, yes, that's good. How do you know that? You can say, I was in Jhevon's class. That's what you want to say. Okay. So this graph looks like the following. It looks like an S, a very elongated S, and it is actually asymptotic to this and asymptotic to that, just like how this one is asymptotic. So it heads towards minus pi over 2, but it never actually attains that level, right? So its range is actually an open interval. The highest part is going to be a positive pi over 2, right? And when you get to calculus, you're going to be considering things like, the idea is like limits. What would happen if your x is going off to infinity? How is this function going to behave? You know, so if you're looking at tangent inverse of x, what happens as x goes to infinity? Pi over 2 is going to be the answer. And what happens if x goes to negative 3? Negative pi over 2 is going to be the answer. Right? And you're going to be expected to know this. That's going to be the graph. Key facts for this graph. Domain is all real numbers. So that one is unrestricted. The range, though, is restricted. The range only goes between not including minus pi over 2 to pi over 2 not inclusive. Of course, tan of tan inverse equals x, and tan inverse of tangent x equals x. And this is for x in not included. Minus pi over 2, strictly less than x, so that's strictly between pi over 2. And this works for all real number x. So once you attain the tangent of a tangent inverse, no matter what that x value is, you just copy that x value over here. It's going to be the same. The other way, though, if the tangent inverse is on the outside, you get only output values in this window. So that's important that you know that. I'll just make a comment here. And these guys really don't even show up in calculus or Calc 2 that much. Like I said, a lot of the things that we want to talk about with inverse trig functions, these three pretty much cover all those ideas. And so I'll just mention here secant inverse, cosecant inverse, cotangent inverse are dealt with similarly. But we'll skip them. And it probably won't be straight for you to skip them for the rest of your calculus career. Maybe you might get that one professor who's like, I want you guys to know everything in the book, you know? And then those exercises that are way at the bottom, like problem number 75, it's gonna have one of these guys. But essentially, dealing with the inverse sine, cosine, and tangent is where we like to live. So you should know the graphs and these basic facts about these things. So another key fact. Is an important concept. Not to get too technical, this is just kind of how you would tend to want to think about things. And for This is just a for instance. I'm just going to use the inverse sign to illustrate what I'm going to say. So when you think of the sine inverse of something equals blah, what is that blah? It's very important that you realize that that output is an angle. Right? So when someone is asking you, evaluate an inverse sine function, or an inverse cosine, or an inverse tangent, it's important for you to have the idea that the output you're looking for is an angle. Because remember, the trig functions work the opposite way. You plug in an angle and you get a number. The inverse trig function, of course, goes backwards. You plug in a number, the output is an angle. Right? So you always think of this guy as being some kind of theta. Right? The output is a theta value. So that's going to be important for you to know. So in other words, when you're using the inverse trig functions, you think of that table in your head as backwards. It's kind of like your input is the inside of the table, your output is going to be one of the pi over 3s or the pi over 6 or the pi over 4s. Right? So the output of this guy is an angle, so you want to think of that. So whenever you're looking for the output of this, you're actually looking at the headline of the table, not the values inside the table. So that's kind of useful to know. This idea is for all trig functions. So, example, if someone asks you, what is the sine inverse of a half? What you should be thinking is, what theta do I plug into sine to get a half? Right? That's how you're thinking of it. What is the angle that I had to put in the sine to get this as the number? Right? And of course, if you remember that table, that's pi over 6. Right? So you'd immediately be able to say, oh, this is actually just pi over 6. Right? Because when I plug in the pi over 6 as the angle, the output is a half. Pi over 6 is in that window minus pi over 2 to pi over 2. So everything checks out. Right? It turns out also that 5 pi over 6 would also work here, but not really, because 5 pi over 6 is outside the window minus pi over 2 to pi over 2. So pi over 6 specifically would be the answer. Right? You wouldn't take all the reference angles. You take the reference angle that falls within the range. Right? So once you're talking about what is the output of an inverse trig function, you have to pay attention to the range here. For the inverse sine function, the range was minus pi over 2 to pi over 2. So technically, there's an infinite number of angles that you'll plug into the sine function and the output would be a half. But for this inverse function specifically, pi over 6 is the only answer, because we have to think of it as a one-to-one function. So that's how the table kind of comes in. But that idea is a very important concept, I think. Just, you want to think of it like that. And you do want to think of this. So that's the question you want to ask yourself. So anytime someone asks you to evaluate an inverse trig function, your mind should be going, what angle should I plug into the regular trig function that's represented here in order to get this guy as the output? And I need to make sure that that output falls within the range window that I mentioned in the key facts for all the trig functions. Let's do, well, we'll start some examples. We probably won't finish them. Finish them next time, or better yet, you try to finish them at home, and then we'll go over them next time. It's quite a few. So, evaluate. And they sometimes ask something like this, maybe in a two-part question, like a part A and a part B. They might ask this as the part B. Next, right? So you should be able to figure these out in roughly 3 minutes, maximum, right? That's the longest amount of time you should take to figure something. So when you're practicing, here's another concept. It's going to be something that you learn, and then it's going to be, you're not going to see it for a while. You're going to kind of forget about it. And then in Calc 2, they're going to hit you with it again. Write something like this. Let's say I take the cosine of the sine inverse of x as a function. So you want to rewrite this as an equivalent function with no trig functions in it. Turns out that that is equivalent to some function that you can write down its formula without the use of trig. So those are the examples I wanted to do. But again, your textbook has many examples. I would really practice a lot of them because this is something you do want to be able to do relatively quickly. Do many more examples. You'll see some in your homework. Do more than is in your homework. Let's see if we can knock out some of these really quickly. Huh? H? Yes, this is a 5. Okay, what's sine inverse of 1? Pi over 2. How do you know? Right, so you're thinking of what angle would I plug into the sine function to get 1 as the output, right? And again, you can look at the table, you can also look at the graph. Pi over 2 is where it hits 1, right? If you look at the sine function, pi over 2 is where it hits 1. So when the 1 is here, you're thinking, what angle did that come from? And of course, you are looking for the angle that lives on this part of the function, right? So you'll also hit 1 over here at some point. I don't care about that. I care about this one. That's where it hits 1. Plugging in pi over 2 into the sine gives me 1, so the sine inverse will give me back the original angle. Sine inverse of minus 1.
Negative pi over 2.
It's what?
Negative pi over 2.
Minus pi over 2. Now someone said 3 pi over 2. Why not? If I take sine of 3 pi over 2, I also get negative 1, right? Why is that not the answer?
Yeah.
It's not in the domain. 3 pi over 2 is over here. You're not on this wing. The answer you give must live between pi over 2 and minus pi over 2 inclusive. 3 pi over 2 is outside this window. So those key facts, they're important. Where I tell you the domain and the range is super important. The output of this will never be outside of the window minus pi over 2 to pi over 2. 3 pi over 2 is outside of this window, so that can never be the answer. Cosine inverse of 2. Undefined. Because what would you ask yourself? What angle should I plug into cosine to get 2 as the output? There is no such angle. The highest cosine goes is 1, right? Cosine never passes 1, right? The maximum it hits is 1. What do I need to plug in for it to hit 2? Nothing. There's nothing I could plug in for it to hit 2. That is undefined. What about tan inverse of 1?
Pi over 4.
What do I plug into tangent to get 1? It is pi over 4. And again, you always have to be thinking in your mind, does this work? Well, yes, because pi over 4 is actually strictly between minus pi over 2 and pi over 2. So that is the one that you want. There will be other things you can plug into tangent to get 1, but they are not going to live in that window. Tan inverse of 0. It's 0. Why? Because I plug in 0 into tangent, I get 0. And 0 is in between here. So 0 works because 0 is in between pi over 2 and minus pi over 2. And at the same time, tangent of 0 is 0. How do I know that? Well, tangent is just sine over cosine. Sine of 0 is 0, cosine of 0 is 1, so I know that's 0. So 0 is the answer here. So let's see, we did like 5 of them in 5 minutes, so it really shouldn't take you long. This is going to be like one part of a problem. You should be spending the majority of your time on it. But they can be a little bit challenging. What about F? So first, what should the output be? Where is this going to live? This is going to give you some theta where your theta lives where? In what window?
Zero to pi?
0 to pi. So any negative answer is never going to be the answer. It has to be somewhere between 0 and pi is what you're supposed to tell me. Think of an angle between 0 and pi where when I plug it into the cosine I get -1/2. It's not undefined. So here's another question you might ask yourself. When do I get +1/2? When do I get 1/2? Because that's something I have memorized.
Pi over 3.
Pi over 3. At pi over 3, that works. Where does this function work? Well, it works between 0 and pi. So there's only the top part of the circle that I only care about. I only care about guys that lie on the top part. What is the reference angle for pi over 3? That's over here. No, the actual angle. Well, 2 pi over 3. Because pi over 3 means divide pi into 3 pieces. There's one section, that's the second section, that's the third section. 2 pi over 3 is the answer. That might be helpful to think of it as a picture. When you're looking for the cosine inverse, the values are actually on the upper half of the circle. So you need to tell me an angle either in the first quadrant or the second quadrant. What you do is you know all the angles in the first quadrant because you memorize them from that table. Then use your knowledge of reference angles to find the answer in the second quadrant. So for example, if I asked you, what is cosine inverse of minus radical 3 over 2? First thing I figure out, where is cosine hits positive radical 3 over 2? I know that happens at pi over 6. However, I want the cosine to be negative. All students take calculus tells me that this is where it's going to be negative. I want the reference angle here. How do I know what that is? Well, I remember what pi over 6 means. That means I divided pi into 6 pieces. I took 5 pieces to get here. That's 5 pi over 6. That is a number between 0 and pi, which when I plug into the cosine, I would get minus radical 3 over 2. Yep.
I'm still confused. Why are you finding the reference angle for cosine? If I don't get it.
I want an angle in the second quadrant. That gives me minus.
Oh, okay. I got it.
So the pi over 6 is the guy in the first quadrant that gives me radical 3 over 2, but that gives me positive. To get negative, I need to be in the second quadrant because cosine is negative over here, and I should be a negative here. So now what I have to do, find the reference angle for that over here. And remember, the reference angle are just the guys that are closest to the x-axis. Right? So your reference angles are going to be either pi over 6, 5 pi over 6, 7 pi over 6, or 11 pi over 6. Obviously, these two are not in play because we're in the cosine inverse. 5 pi over 6 is the guy. So whenever here I have a positive number for the cosine inverse, I'm looking in the first quadrant. Whenever I want to get a negative number, I'm looking for its reference angle in the second quadrant. For the sine inverse, when you're thinking of sine inverse, you might want to look at the picture here. What you're looking at is the right half of the circle. You're looking for all angles between minus pi over 2 to pi over 2. So someone can ask you, sine inverse of minus radical 2 over 2. Okay, what gives me positive radical 2 over 2? Pi over 4. What's the reference angle for pi over 4 down here? Well, minus pi over 4. That is a number that's between minus pi over 2 and pi over 2, where the sine output is going to be negative because all students take calculus. Sine is negative here. So once I see a negative number, it means I'm looking for something in the fourth quadrant where it's measured in the negative direction. So I know I'm doing it kind of quickly, but there are actually a lot of concepts coming to you. You really have to know everything I mentioned last class very well. Like the tables should be like, you should be on point with memorizing the table, should be on point with what a reference angle means, all that stuff. Like, so you'll have to put that all together for problems like these, but ultimately you should be able to do it pretty quickly. That's why I put over here, do many examples. It'll take some getting used to. But we'll stop there for now. We'll finish up those examples and then do addition and subtraction, double angle formulas and all that stuff. Also, whatever I covered up to today is what you're responsible for on the test. Anything else we cover is like extra. I'll push it to the bonus. Because our next test is Wednesday. Probably Monday. So we're going to work on it over there. Yes. That I got from this. Oh, yeah, well, I guess by tonight or early tomorrow. I'll probably extend from the graphs and inverses. I did actually take it.
I hope you know your camera's still
Oh,
yeah.
It is soft.